Hello everyone, good afternoon. I am Manoj Natarajan doing my masters at Dalhousie University and working as a student at Agri and Agri-Food Canada Lethbridge Research Centre under the supervision of Dr. Kesav Singh. Today, I am going to present on the topic developing a low-cost digital imaging system for plant phenotyping using Raspberry Pi computers. Traditionally, phenotyping in plant breeding is time-consuming, labor-intensive, and the database is insufficient to satisfy the need of plant breeders, which hamper the breeding progress. In recent years, advances in digital electronics and sensor technologies in agriculture have aided in the development of innovative methods for measuring plant phenotypic characteristics. In this study, the Raspberry Pi based automation system was integrated with the image sensor Sony IMX219PQ CMOS 8MP camera in growth chamber to timely monitoring the crop growth parameters in wheat breeding trial for plant phenotyping. The Raspberry Pi system was programmed using open source Python scripting to capture highly resolution multiple images in user defined time interval approximately 4 hours throughout the experimental cycle. These images allow us to study about the morphometric phenologies such as plant structure, height, density and volume, canopy cover, leaf area index, anthesis, timing, maturity and digital biomass and other physiological parameters which represent overall plant growth and health. Moving on to materials and method. Hardware used. In the study, the main hardware of sensor system is from Raspberry Pi module 3B and 4 quad-core 64-bit and 2 GB RAM as a microprocessor to control the image capturing techniques. The Raspberry Pi modules were connected to Raspberry Pi camera version 2 RGB via camera serial interport on the Raspberry Pi microprocessor. These camera sensors are based on image sensor 8 megapixel and the active pixel count of the camera is 3280 into 2646. To manage the lack of Wi-Fi availability, a real-time clock were used to determine the correct timing of image capture. A 5-volt electrical fan were also used to control the heat dissipated from the Raspberry Pi as it running continuously. The Raspberry Pi modules were powered by 26800 mAh solar battery which can be directly connected to AC or solar light. Software used. Linux-based operating system Raspbian Buster was running on the Raspberry Pi microprocessor and open source Python 3 was utilized as the primary programming language to command the board and the camera to capture the image at user-defined time point. Necessary libraries were installed to create a time-lapse imaging algorithm to capture the image at every 4 hours time interval. Initially, the program was automatically adjusted for white balance, brightness, maximum image resolution, frame rate, exposure mode, shutter speed associated with the variable growth chamber lighting condition. We programmed the camera to capture snapshot with a 3-second delay between each shot, thus a total of 5 shots per time point. Therefore, from the Raspberry Pi board, system could capture 30 images in a day. As the real-time clock of Pi was synchronized with the Raspberry Pi system, a timestamp for each captured image was recorded and saved as a specific file name on the secure digital SD card. The camera system was scheduled to power on automatically through the power management system. Similarly, the time-lapse imaging script ran automatically using Linux cron tab schedule time. In this study, the camera was controlled and the time-lapse script was used to at the following 6 time point each days. Therefore, for 1 cycle at each time point, the sensor system was set to on before running the script for 15 minutes and power off after running for 15 minutes to ensure all the operations are completed. Moving to experimental setup. The experimental setup for plant phenotyping wheat crops was carried out in the growth chamber at Agri and Agri-Food Canada Lethbridge Research Centre AB. The growth chamber has two sides where first cells were installed with 5 Raspberry Pi module to capture the digital images. Figure 4 represents the one side of growth chamber and figure 5 shows the mounting view of Raspberry Pi module. The Raspberry Pi and its peripheral device, which is solar power panel, were tied and zip tied using with the velcros and others on the cells. The camera was set at 170 cm above the ground level which is the table length as shown in the figure 5. Each cell has 16 plants with the marked dimension of 127 into 127 centimeter per cycle. Result and discussion. The proposed experimental setup is able to capture 30 images in a day. The Wi-Fi hotspot was used for data transfer from Raspberry Pi to laptop. Then the image processing software were used to analyze the data offline captured by the Raspberry Pi computer with the following 3 steps. Object segmentation. Segmenting the plant region in the image capture. Plant extraction. Extracting the plant leaf in the image capture. Morphology. Analyze and process the extracted plant pixel based on the shape, which help to determine the plant structure and growth. Conclusion. The Raspberry Pi system found promising to automatically capture spatio-temporal images of the plant growth. The images has been analyzed to extract the morphological feature and physiological characteristics of plant. These studies suggest that the developed low-cost digital imaging system can be integrated with Internet to facilitate Internet of Things based sensor system, which help the plant breeders to make timely decisions on monitoring the crop in real time. The references are listed here. Acknowledgement. I would like to thank the Agriculture and Agri-Food Canada for supporting the ABAS and WGRF project. We acknowledge the Lethbridge Research Center Winter Cereal Group member for their supporting in setting up the experimental to conduct these studies. Funding from the following institutions are greatly appreciated. Thank you.